All right, good morning. So here we are yet again for yet another lovely session of MENG 3310 Fluid Mechanics. And today we're going to be working through a few examples of working with Reynolds transport theorem, control volume, and a little bit as well on velocity and acceleration fields. And in the previous lectures, we've introduced these topics and worked on some basic properties of them. But today, all I'm going to do is work through a few examples from this material. This is going to be the 13th video in the series, and it's covering some of the remaining material from Chapter 4 of the Munson text. All right, so first problem, problem 1. Problem 1. The first thing I'm going to say is, okay, so let's just go to our old given, find, etc. format. Given. A flow field has the following velocity profile, or velocity vector. A flow field has the velocity vector v equals negative 2xyz over x squared plus y squared squared I in the I direction plus x squared minus y squared z, x squared minus y squared z divided by x squared plus y squared quantity squared. All of this in the j direction, plus y over x squared plus y squared in the k direction. Y over x squared plus y squared in the k direction. So this describes the fluid velocity as it varies in x and y and z. And fundamentally what this means is if I put in coordinates x, y, and z, it will show me a certain those points will correspond to a location in space. And then putting in those locations in space, those x, y, z coordinates in the x, y, z plane, So again, x, y, and z. So if I put in a certain location, x, y, and z, this equation will then give me a certain vector in the ijk direction. It will give me a certain vector for that location. And if I put in a different x, y, z, maybe I can do something like v1 here, and then x1, y1, z1, x1, y1, z1, and then if I have another point down here, perhaps x2, y2, z2, it would give me a different v2. And if we wanted to, we could plot this out in 3 dimensions and actually model the vectors out, etc., model the flow field out, etc. But this is the basic idea behind an equation like this. Okay, so all of this is given, and we are asked to find the acceleration vector for this flow field. Find the acceleration vector for this flow field. Of this flow field. And then we're going to use this relationship here. All right, so the relationship we're going to use is as follows. The acceleration vector, I hope you like partial derivatives, so I'm going to do this on the next page to sort of illustrate, to sort of give myself a little more room. So, well, let's see this. So we know the velocity vector, so let me maybe mark solution here. And the velocity vector is, of course, ui plus vj plus wk here. And I'm going to use the acceleration vector. We're going to find the acceleration vector via a series of partials. So it's going to be the partial of u with respect to t plus u times the partial of u with respect to x plus v times the partial of u with respect to y plus w times the partial of u with respect to z. All of this in the I direction. And you can find this formula in the text as well. And then plus, in the j direction, the partial of v with respect to t plus u times the partial of v with respect to x, partial of v with respect to x, plus v times the partial of v with respect to y, plus w times the partial of v with respect to z. And all of this in the j direction. Plus, then, in the k direction, the partial of w with respect to time, or with respect to t, plus u times the partial of w with respect to x, plus v times the partial of w with respect to y, plus w, plus v plus times the partial of w with respect to y, plus w times the partial of w with respect to z. And all of this in the k direction. Okay, so if we run through this, and we also know that the partial of v with respect to t is equal to the partial of v with respect to t is equal to the partial of w with respect to t, and this is equal to 0. All right. Well, if I were to try to actually run through this by hand, what would be the problem? What would be the problem if I tried to run through this all by hand?
Very lengthy.
It would be very, very lengthy, and it would involve many, many pages of calculations, and it's almost likely that I would probably make a mistake somewhere, almost inevitable. So this is actually an illustration of, this is the type of problem you probably want to solve via a computer, because you're going to be multiplying w's times partials, you're going to be multiplying u's times partial of u's, all of these things, and this is really the type of problem that's best solved via an algebraic package similar to Maple or some other Wolfram Alpha perhaps, or other form of computer-based calculus or algebraic software. So I'm going to write the answer, but in reality, this is the type of problem you probably won't want to do by hand. This would take probably a class period or two to work all the way through. So I will illustrate the final result, but really this is the type of problem that you want to solve via a computer program. Because again, if I run through the partial of u with respect to t, even that's going to take a bit, it won't take that long, but then combining and multiplying and adding all of these things together and solving for common denominators and all this kind of thing, this is going to take a very long time. So that is something you want to keep in mind. So the nice thing about doing this is I can just say, using the magic of computer software, this will produce the final result. AX, the acceleration in the x direction, is going to be 4xy squared, z squared, times y squared minus 3x squared, divided by x squared plus y squared to the 5th power, minus 2xz times x squared minus 3y squared times x squared minus y squared divided by x squared plus y squared to the 5th power. And then minus 2xy squared over x squared plus y squared to the third power. And then a and the y, ay, is going to be 4x squared yz squared times x squared minus 3y squared over x squared plus y squared to the fifth power. To the fifth power plus 2yz squared times x squared minus y squared times y squared minus 3x squared. Isn't this fun? Divided by, I didn't say we were done yet, x squared plus y squared to the fifth power, another one of those, minus y times x squared minus y squared over x squared plus y squared to the third power. To the third power. And then finally, in the z direction, equals x squared minus y squared squared times z divided by x squared plus y squared to the fourth power. See? Simple. All you gotta do is take the derivatives. Very easy, right? Sure. Anyway, conceptually, it's not that difficult. You just, I think y'all know how to run, I think at this point, you all know how to run through a partial derivative. I mean, really, it's not that difficult running through partial derivatives. It's just tedious. I mean, this stuff, when I showed you the formula on the previous page, this really isn't that, conceptually, it's really not that difficult. You're just running through a bunch of partial derivatives and multiplying them together. What it is, however, is very time-consuming and tedious. So, something like this, if you were curious about how I might test you over something like this on an exam, one, I would either give you the problem, maybe I would give you the problem and maybe I'd give you a simpler problem, maybe something that wouldn't be quite as long and you could work it out in a shorter length of time. Or more likely, I might just ask you to set up the formula or something like that. I wouldn't have the time to ask you to run all the way through the partial derivative for a problem this complex in a simple hour-and-a-half exam, unless I wanted this to really be the, I cannot talk, it's Friday, unless I wanted this to be the only problem that you would be working on during that period.
You guys a take-home problem like this?
That's a good idea, take-home problem. Anyway, we'll see. Anyway. All right, so let's move on. Okay. So let's look at problem number 2 now for today. And this is going to be problem 4.68 in the text. Problem 2. So, the wind blows across the field. Wind blows across a field. Across a field with the velocity profile below. With the parameter b equal to velocity. The parameter that we're going to be analyzing equal to velocity. Equal to velocity. Or I should maybe make this a period and a comma and a capital. With the parameter b equal to velocity, determine the momentum flow rate. The momentum flow rate across vertical surface AB, which is a unit depth into the paper, which is unit depth into the page, or into the screen here. Basically, we're saying it has a depth of 1 perpendicular to the screen. So let me draw this out here. And so we're going to have a flat field, and there's going to be a velocity profile like shown. So up to a certain height, it's going to be linearly increasing. And then beyond that, it's going to be constant. And up here, it's 15 feet per second, and then it will decrease to 0 at the ground. 15 feet per second, and then this height transition is at a height of 10 feet. Now this is a simplification of how, this is going to be a simplification of how winds actually behave, but they do illustrate this kind of velocity profile, although they tend to be more parabolic or something like that, and more of a smooth function. So their actual velocity profiles in real life tend to be something like, you have something near the surface, but then, well, actually right at the surface is going to be 0, but it's kind of something a little like that, more of a smooth function, like this. But that's not important for this problem. If you ever wonder why wind turbines on wind farms, wind power plants, why they're elevated high above the ground on those very high stalks, the reason for, or those very high columns, the reason is that you have higher, more steady winds the higher up from the ground that you are. And in fact, some people have actually investigated or actually looking into or proposed before using sort of like flying wind turbines. If you could imagine, if you could put a wind turbine up at, say, 10,000 feet and tether it to the ground via a rope or something like that, or a steel cable or a Kevlar cable or something, and then you just have effectively a kite with a big sort of metal kite with a wind turbine on it. You could theoretically generate a great deal of power from very high altitude winds with a much smaller device. But anyway, something interesting to consider. Now, it does also define surface AB. We have A here and B here, and this 15 feet per second just continues upward indefinitely. And this AB here, so this is surface AB, and it has a height of 20 feet. And it also tells us that we want to integrate it this way, and it also gives us that the normal vector n outward here is going to be equal to the I hat direction. Okay, so jot that down if you could, and then we'll start working through the integration. So questions on what we're doing. Again, what we're going to be looking at is we're trying to find the total amount of momentum per second that is flowing through this. I should maybe show an arrow there too. I'm trying to find the momentum per second that is flowing through this surface. So that's what I want. That's what I'm going to do here. And because this is in feet per second, I'm going to use English units for this. Now, also keep in mind that because we're looking at the we're going to be looking for the extensive, not the intensive property. We're not going to be looking for the lowercase b. We're going to be looking for the uppercase b. So let's think about this. Let's work through this solution. All right, so B dot AB, the flow rate of our extensive property, is going to be equal to the integral of across surface AB, the surface integral of rho B, vector B, times velocity V dot n dA. So this is the surface integral. And this is then equal to, if I want to change this into a, oh, sorry, this is actually, sorry, I think this should more be a volumetric flow rate. Maybe something more like this, I believe. Yeah, that would make more sense. Sorry about that. Okay, dot n dA, I believe, sorry, actually, I was right the first time. Derp, sorry. That's velocity. Okay, sorry about that. Now, then I want to do so if I look at this then, the flow rate, if I'm going to change the, momentum into something a little different. So I'm going to do the integral AB times rho VV dot n dA. Dot n dA. Okay, and this is changing. This is how I'm changing. Okay, so here's the thing. If we think about this, the momentum is kilograms meters per second, right? And if we change this if we're looking at this in terms of, so the overall momentum flow rate would be something like kilograms meters per second. And if I look at this in terms of its intrinsic property, in other words, divided by mass, if I take kilogram meters per second and divide by mass, I effectively get just meters per second or simply velocity. So that's why I can say if the extensive property is momentum flow rate, the intensive property, the momentum per unit mass is simply velocity. So that's why I have two different velocity V's here. And then this will be equal to, the rho is going to be constant, so I can take that rho out. It's going to be integral AB. And AB more specifically is, I'm going to do an integral with respect to y, and I'm going to take it from y equals 0 to y equals 20 feet. And it will be equal to VI times VI dot I. V times the component of V times I, or the magnitude of V times I, for each of these dotted into I. Times then a depth of 1 foot. Times, and then with a dy. Or this will also be equal to rho I hat, integral from 0 to 20 of v squared dy. However, so I need to note, but the v is not constant. V equals 15 over 10 y feet per second, for y is between 0 and 10, and v equals 15 feet per second. So I'm going to have to break this thing up, in other words. 15 feet per second for y is greater than or equal to 10 feet. Thus, I can break this surface integral into two pieces. Thus, b dot AB is equal to rho I hat, rho times I hat, times the integral from 0 to 10 of 15 over 10y squared times dy plus the integral from 10 to 20 of 15 squared dy, or Or then, well, if you run through all of the integration, this comes to, oh, let's see. If I run through the density, if I use a density of air of 0.00238 slugs per cubic feet, slugs per cubic foot, slugs per cubic foot times, 750 to the fourth power seconds squared plus 2,250 feet to the fourth power seconds squared. In the I direction, well, in the end, when we combine all this together, we will find that this is 7.14 I slug feet per second squared, slug feet per second squared, or is simply equal to 7.14 I pounds. So momentum flow rate can actually be conceived of as a unit of pounds. 7.14 I pounds. What a lovely problem. Okay, so again, what I'm doing is I'm looking at the surface integral. I'm saying that I'm breaking this into its constituent pieces. This is going to be the actual velocity vector, and this is going to be the velocity vector dotted into the coordinate component, the normal component of the normal direction of whatever surface I'm integrating. So that's why that's basically the way the math works out. I'll let you review that a bit some more. But do you have any questions on that? I know that can be a little dense, but what we're doing, so fundamentally how this is, the way to look at this is, here I am taking the momentum just in general in the I direction, and here I'm taking the momentum here I'm taking the velocity just general in the X direction, and here I'm taking the velocity that is in the same component as the normal vector. So remember, dot product gives you the component that is in the direction so the dot product gives it the projection of one vector onto another. So what I'm trying to do is I'm trying to find the momentum that flows through this surface here. So I'm not interested in any other momentum this thing has. I only want the velocity that is entering through here. Now, in this case, it's going to be fine because there is no there's no vertical component to the velocity, but I would still need that dot product just for completion's sake. All right. And I think I have time for one more problem, and I'll work through this one fairly quickly if I can. And this one is going to be based on a conservation of momentum. All right. So this one is going to be based on a moving control volume. So this is going to be a little interesting. I have a moving control volume. So let me show you what we have given. I have a fire hose or a hose or a nozzle that is being fired into an open cart of water. This is going to be a little screwy, so bear with me for a moment. I don't know why you would do such things, but I suppose you could. Actually, this reminds me of one of those carnival games or something, but... Okay, so... let's see. Let's see. Now, so let me, how might I describe this? So I'm trying to think of a way to quickly draw this. So essentially what I have is this kind of cart thing here. And it has some tires or wheels or whatnot. and I am firing a stream of water into the container. So let me show the nozzle here. So I have a nozzle here that is firing a stream of water into this container. And it's not just any generic fluid, it is water. So it's going to go in here, it's going to splash around and be deposited into the container. Okay? Okay. Okay, so let's see. We have this, and this stream of water has a velocity of 10 meters per second, a velocity of 10 meters per second, and a stream diameter of 0.1 meters. Stream diameter of 0.1 meters, 0.1 meters, and we have a moving control volume, as shown. We have a moving control volume here. A moving control volume here. And the distance initially from the cart to the hose is 3 meters. 3 meters. And initially this cart has a velocity towards the hose. V naught equals 2 meters per second. 2 meters per second. And again, this is a moving control volume. And however, let's say this is the system at 2 meters per second, at time equals 2. So the stream, let's see, so let me just sort of write out the description here. So water flows from a nozzle with a speed of 10 meters per second and is collected in a container that moves towards the nozzle with a speed initial of 2 meters per second as shown. The control surface consists of the inner surface of the container and the system. So this is here, the control volume and our system are going to be different. So control volume is the inside of the container. So this is really illustrating the difference between control volume and system. Inside container. The system, however, and it is, the system then is the volume of water, is the water itself. It's the water in the tank and in the air. So we're defining our system as all of the water that's in this stream and all of the water that's been collected in the tank. So this one's a little bit screwy. Because of that, our control volume is not, does not directly correspond with our system, as weird as that sounds. The control volume is not going to directly correspond with the system. And so at time there, and then I'm going to say at time t equals 0, or sorry, at time t equals 0, again, okay, so actually I should specify a little bit more. The system is the water in the tank and in the air at time t equals 0. So any water that leaves the nozzle after t equals 0 will not be part of our system. Any water that leaves the nozzle, after t equals 0 is not in system. Is not part of the system. And then, so, and what we are asking for is find, this problem took way too long to set up, find at time t equals 0.1, at time t equals 0.1 seconds, what volume of the system remains outside the tank let's see. So A, at time t equals 0.1 seconds, what volume of the system remains outside of the control volume? Remains outside of control volume. Of control volume. And B, how much at that same time how much water has entered the tank, or how much water has entered the control volume. H2O has entered control volume. Has entered the control volume. Has entered the control volume. So we're going to try to find at t equals 0.1 seconds what volume of the system, or in other words, the initial water that was in the air and in the tank at 0.1 seconds remains in there and remains outside the tank, or remains outside the control volume, and at the same time how much water has entered the control volume during this period. All right, so let's solve that. So solution here. All right, so let's see. During the time interval now, let's see. And also one thing to keep in mind is they didn't give us the mass of the tank, so we're going to have to assume that this thing moves at a constant velocity. Or I'm going to have to assume that this thing moves at a constant velocity. I don't know the mass of the tank, so therefore I can't sort of predict how the velocity of the tank will change. So I'm going to assume that the tank is heavy. Maybe it's made of cast iron or something. It's a very heavy tank, and it's going to be moving at a constant velocity, or maybe it has a motor in it or something like that. So during the time interval delta t, the control volume moves to the left, left a distance of v control v, that's velocity of the control volume, times delta t equals 2 times delta t meters. And the water that was at the nozzle exit, moves a distance v delta t equals 10 delta t meters to the right. So if I were to draw this out then, here, if I'm going to draw this out, shown below, so this is our control volume. In fact, I'll draw it in blue to show that it's water. This is our system, I should say. So this is going to be at here. I'll draw it out kind of like this here. And this is the part of it that's in the tank. And our control volume then is like here. Our control volume is moving. However, our control volume used to be here. The initial location of the system and the control volume were here. So this is where the control volume used to be. This is CVT equals 0, and this distance, and let me just mark all these with a little key over here. This is system T equals 0.1, or T equals delta T perhaps. No, I'll do it delta T, that's fine. We can do this for any T. System D equals delta T. In the red, I have the control volume at T equals delta T. And then maybe in green here, maybe in purple, I have the overlap, something more like this. This is the part of the system that is no longer present, or that has moved on, because we were looking at the volume. Originally the nozzle was here, or sorry, originally this chunk of water was here. This is the system at T equals 0. And so the overlap here then, let me label these, is 10 delta T, and this one is 2 delta T, 2 delta T, and this is 0.1 meters. And the distance from here to here is going to be 3 minus 12, 3 minus 12 delta T, and we'll get that. So that's actually at, let's see here. That's not quite right. Okay, we don't need that one. That's for there was a second portion of the problem that I won't be doing, so we don't necessarily need that one. Okay. So, let's see. So the amount of, what I can do then is I can solve this and simply get to this fairly quickly. The amount of the system outside of the control volume at time t equals 2, that looks like an L, at time t equals 2 seconds, t equals 0.1 seconds, well, it's going to be pi over 4 times 0.1 squared. This is the area of this cross section, times, let's say, actually, and you know what, I was actually right there. This should actually be, that's 3 meters, right? 3 meters here, and that's where this is coming from. Sorry, I was a little, wasn't being very clear on where that was coming from. So let me just mark here. This actually does make sense. Sorry about that. I was getting myself a little confused. And this should be 3 minus 12 delta t. The original length was 3, and then we're subtracting 12 delta t. That is the combined velocity between them. So that will help us work along. Sorry for the confusion. 3 minus 12 delta t meters for the length between the end of the fluid stream at the end of our system and the start of our control volume. Okay, so then, if I can quit jumping around.
I have a question.
Yes.
Isn't the cart moving towards the nozzle?
Yes, the cart is moving towards the nozzle, so it's going this way.
And the stream, and that 10 delta T is going opposite.
This is just the original state. I'm not drawing things in motion. I'm just showing the initial and the final conditions. So I'm not trying to draw this in motion. I'm just showing the initial and final conditions. And so then this is times 0. So this is the cross-sectional area. times a volume. So really all I'm doing here is finding volume. Minus 12 delta T, all of this meter cubed. So this is the volume outside the control volume, the volume of the system outside the control volume. And this is 0.0141 cubic meters at T equals 0.1 seconds. And then the second part, so that's A, and then B, during the delta T equals 0.1 seconds. So basically, if I want to conceive of this a little differently, the volume, if I want to, for parts A and B, if I want to find the volume that is outside the control surface, all I have to do is find the volume of this cylinder here. If I want to find the volume that has entered the control volume during that time, all I have to do is find the volume of this cylinder here. So I know I'm making this sound a lot more complicated than it is, but really this is fairly straightforward. All I'm doing is finding the volume of I'm drawing it out and then finding the volume of two different cylinders. So this then is going to be pi over 4 times 0.1 squared times 12 delta T meter cubed, which will equal 0.00942 cubic meters has entered the control volume. And then this one is outside of control volume. Is outside of the control volume. All right, any questions on that? Okay, hopefully that's fairly straightforward. I know it was a bit over time today, but hopefully that clears a few things up, or hopefully you've learned something. Or if you don't, or if you haven't, please, if you have any questions, feel free to stop by my office hours. Thank you for tolerating the lateness and technical difficulties today. I'll be posting a lecture for Monday later today, and as always, thank you.